In this lesson, we discuss directional derivatives. Just from the beginning, let me make this assumption that all the functions that we discuss today will be differentiable functions, and we are focusing on only differentiable functions. So let's see what is directional derivative. So far, when we have a function of f of x and y, we have talked about partial derivative with respect to x, or the other way we showed that, this way, and partial derivative with respect to y. In fact, when I differentiate a function with respect to x, the direction is the positive direction of x-axis. And when we differentiate a function of two variables with respect to y, the direction is the positive direction of y-axis. But what if we are interested in knowing the rate of change in some other direction? So the given function that we have, we want to know that if we have another direction other than a positive direction of x-axis or positive direction of y-axis, what would be the rate of change? That's where the directional derivative comes into play. So in fact, partial derivative of f with respect to x and partial derivative of f with respect to y are two directional derivatives. Just two of them. And there are infinitely many directional, at any point, we have infinitely many directions in the plane. So we can consider any other direction and find the directional derivatives. So today we want to find directional derivatives in a given direction. So these two are two of the directional derivatives. As I explained, partial derivative of f with respect to x is with respect to the direction of the positive direction of x-axis, and partial derivative of f with respect to y is in the direction of positive direction of y-axis. But we might have other directions. Okay, now let's see how we define a directional derivative. Again, I assume that all the functions are differentiable. So throughout the discussion, I assume that all the functions are differentiable. Okay, so instead of writing in statements, in sentences and a statement, let me just see what assumptions do we have. We have a function of two variables, f of x and y. At a given point, AB, a given point AB, and a direction. And a direction which is in this context is given by a unit vector. A direction given by a unit vector u. So for a function f of x and y, a given point a, b, and a given direction u, we want to define the directional derivative. And here is the definition. It is a limits. Definition is again by limits as h tends to 0. To set up the definition, I need to write two coordinates for the vector u. So the vector u has two coordinates, u1 and u2. So u is a vector, and it has two coordinates, u1 and u2. So that's how the directional derivative is defined. It's the limit of f of a plus h times u1, comma, b plus h times u2, minus f of a and b divided by h. Let's see what this says. It says that if we move a little bit from AB to some other point in the direction of U1, U2, multiplying H by U1 and A2 simultaneously and adding to A and B guarantees that we move in the direction of U. But as H tends to 0, it means that we are very close to the original point A and B. But what does this difference, if a difference quotient measures? It measures the rate of change for the function of f in the direction of u. So this is the instantaneous rate of change of f of xy at the point AB in the direction of u, of the vector u. The standard notation that it is it denotes this directional derivative by is a capital D standing for derivative, a little u here on the lower right corner of D, meaning that it's in the direction of u of f at the given point AB. That's how it is denoted. So this directional derivative tells us that how fast or how slow a function increases or decreases at a given point in certain direction. But of course, computing the directional derivative using this definition is a little bit long, and instead of using the definition, we use a formula or the theorem that I stated as a note, and that will be helpful to find the directional derivative, to compute the directional derivative. So in fact, the directional derivative of f at the point AB in the direction of vector u is calculated by the dot product of two vectors. So the answer is a number. You know that the dot product of two vectors is a number. The first vector is partial derivative of the first coordinate of the first vector is partial derivative of x at point AB. And the second coordinate is partial derivative with respect to y, point AB. The other vector is u1, u2, or this is vector u with coordinates u1, u2. So the first vector has two coordinates. The first coordinate, partial derivative with respect to x at the given point AB. The second coordinate is partial derivative with respect to y at the given point AB. This vector is dot product with the other vector, vector u, consisting of coordinates u1 and u2. So this note, just let me write an easier way to compute directional derivatives. Or it could have been stated as a theorem. So let's see an example. Let's see an example. So we want to compute the directional derivative so we need a function given, so of f of x and y is x squared plus 3xy. We need a point. At the point, suppose the given point is 0.21, and we need a direction which should be given as a unit vector. If the given vector is not a unit vector, if the length is not 1, we need to divide that vector or both coordinates of the vector by the length of the vector to make it a unit vector. But in this example, the given vector is a unit vector. So, and the two, so in the direction of unit vector, the unit vector is 1/2 and radical 3/2. So the formula that we had from the previous page to find the directional derivative is I should find this dot product, the dot product of partial derivative of f with respect to x. At what point? At the given point 2, 1. Partial derivative with respect to y at the point 2, 1. It should be dot product by the unit vector 1/2 radical 3/2. The number that we get at the end tell us that how much will be the rate of change for this function at that point in that given direction. So I need to find, to be able to compute these two, I need to find partial derivative with respect to x at any xy. At any xy, partial derivative with respect to x, knowing that f of x and y is x squared plus 3xy. With respect to x is 2x plus 3y. So partial derivative of f with respect to x at the given point 2, 1. So at the given point 2, 1. Here, a substitute 2 for x and 1 for y. I'll get, excuse me, I'll get 7. So in fact, this coordinate of the vector is 7 by this calculation. For the other one, I need to find, we find a partial derivative of f with respect to y at any xy. F of x and y is x squared plus 3xy. The partial derivative with respect to y is just 3x. So evaluated at the given point 2, 1. x2, y1. 3x has no y, so that 1 doesn't do anything. Only x is 2, so 3 times 2 gives me 6. So this second coordinate is 6. So to answer this question, I need to do the dot product of this vector and this vector. We know from the discussion that we had before about the dot product, to do this, first coordinate times the first coordinate, 7 times 1/2 is 7/2, and plus second coordinate times second coordinate, 6 radical 3/2. You don't need to simplify the second one because now common denominator in fact is 2, and 7 plus 6 radical 3.